My name is Joseph Mangun, and today we're going to be looking at whether we can get new drugs from an old plant, specifically new anti-malarials from Artemisia annua. This is my presentation, and for clarity's sake, we'll be going through each section one at a time. Starting with the introduction, malaria is responsible for over 200 million cases a year, and in 2018 it was responsible for 405,000 deaths. Obviously, with numbers like this, there's room for improvement in terms of treatments, and complementary treatments could be used to help improve some of these cases. The idea in this project is preliminary evaluation suggested there was something in Artemisia annua, an unknown component that had anti-malarial activity in addition to what was known. And the goal is to identify it, assign it a structure, and a probable mechanism of action. The basic method for extracting the material was to begin by exposing it to solution and allowing it to separate on polarity, and then using partition and chromatography to further separate it based on finer and finer gradations of polarity so that it could be purified to a greater extent and worked with in a more realistic way. So the basic workflow was to start with the crude extract, do the extraction, partition, and a chromatography, and then ultimately, once you have your fractions, to be able to work with those to perform other methods such as mass spec or other statistical analysis based on the fractions that you've obtained. Here on the top left, you see the main component, that's the known constituent of Artemisia annua, that's anti-malarial, which is artemisinin. And you can see in the top ring structure in the middle, there's a peroxide bridge, which is fairly unique, and that's what's largely responsible for its anti-malarial activity, as well as you see other analogs here. And the idea of the project is to figure out what this new unknown is, whether it has this mechanism or some other mechanism, and to try and give a structure to that unknown compound. And then there on the bottom, you see just another perspective that the peroxide bridge is over the ring structure. This is the chromatography results. You see over there on the right, in %B, there's two solutions. And the difference in polarity of the solutions affects how fast, how quickly the sample will pass through the column. And so the idea is you use those differences in polarities to achieve differences in elution time. And so you can see that the other line, so the blue reflects %B, which is hexane or methanol, and then A is chloroform. And so the other lines reflect the detectors of light, which is essentially different frequencies. So the different colors correspond to different frequencies, and the height indicates the concentration of whatever is being detected at that frequency. So it gives you an idea of not only when something is coming out, but how much is and what frequencies of light were being absorbed. This is just a sort of visual representation of that color separation I was talking about, and you can see how the machine created a sort of gradient as it was creating these fractions. And then on the left is just what the machine indicated it did as well. So in terms of future plans, we're going to, now that we know, well, we have some unknown component that's responsible for some of the anti-malarial activity, we want to assign it a structure. So we're going to be taking our fractions and running mass spec on them to hopefully identify some of the components, maybe actually, if we're lucky, the entire structure. Possibly we'll see that endoperoxide bridge, or maybe we won't. We can also run PCA, which is a statistical tool, and essentially looks at, when you have a multivariable problem, which variables are most responsible for something you're interested in. Here we're looking at which components of Artemisia annua are most responsible for anti-malarial activity, and that'll be another way that we can help look at it once we start breaking down into different fractions. Based on the results of that, we could potentially identify the structure and hopefully some plausible mechanism of action, and then look into hopefully the creation of a drug lead. Again, my name is Joe Mangun, and thank you for watching my presentation.